Okay. Okay, so let's start then. So okay. So let's see where we are. So we talked about cat kappa spaces. We gave characterizations of cat kappa spaces. Oh, I should just say one thing. This last characterization using angles, I mean, as this is a sufficient condition for cat kappa. It's not a necessary condition that you have an angle function so that the angles are less than or equal to the comparison angles in M2 kappa. This can be used to show that any tree is cat kappa for any kappa, right? Because in a tree, so if X is a tree, then it is cat kappa for all kappa less than or equal to 0. Because in a tree, if I take a triangle, a geodesic triangle, then it's a tripod. And so if I take the Alexandrov angle, between the geodesics PQ and PR, what will this Alexandrov angle be? What will the Alexandrov angle be?
0.
0, right? Because if I take 2 points here on this geodesic and this geodesic, the Euclidean triangle, I have equality in the triangle inequality, right? So the angle at P will be 0, right? In the Euclidean triangle corresponding to this. And the Alexandrov angle is a limb sup of such angles. So it will also be 0, right? So this will be less than or equal to the comparison angle. Is this clear?
Yes.
Okay, so this gives a short proof that a tree is cat kappa for any kappa. Okay. Using the Alexandrov angle. Okay. All right. Now, last time I stated the Alexandrov's comparison theorem that if M is a complete Riemannian manifold, which is simply connected and has sectional curvature less than or equal to kappa, where kappa is less than or equal to 0, then M is cat kappa, right? Okay, so that's what we're going to prove. So for that, we need to talk about the n-dimensional hyperbolic space. So we defined it initially as the upper half space in Rn, where the last coordinate xn is positive. And the metric was similar to the two-dimensional case. It was the Euclidean metric divided by the height xn squared. And then we got isometries of 3 types: translations, horizontal translations, scalings, and rotations around the origin in the first n-1 coordinates, fixing the height. So these were isometries. These acted transitively on Hn. And then we defined a map to the unit ball. And we saw that under this diffeomorphism to the unit ball, the metric on the hyperbolic metric on the upper half space becomes a metric on the unit ball 4 times the Euclidean metric divided by 1 minus norm x squared whole squared, which is just like the formula in 2 dimensions, right? For the hyperbolic metric on the unit disk. So this is the unit ball model of the hyperbolic space. So this is how we define this map, right? So first there was a scaling, x goes to half x. Then there was a vertical translation by half. And then there was inversion in the unit circle. And then there was a vertical translation by -1. Okay, so it was just a composition of these diffeomorphisms. So under this, if I look at, let's say, a vertical line here through the origin, a vertical radius, the vertical radius, okay, then that will go to a vertical radius in this ball of radius half, and then that goes to a vertical radius in after translation. Then after inversion, this vertical radius is a line passing through the origin, so it goes to itself under inversion. So it will go to a vertical line, right? All right, passing through this point here at height 1. Yes? Okay.
Yes.
And so then when I translate down, I'll get a vertical line passing through the origin, right? Is that clear? So this one radius here goes to a vertical line here. Is that clear? Yes?
Yes.
Okay, this vertical radius here will go to a vertical line here under this isometry. Okay. So why are we interested? Because like we showed in 2 dimensions, the vertical lines were geodesics in the upper half space. Similarly, in n dimensions, the same argument using the retraction principle, right, of Thurston, shows that all the vertical lines in the upper half space are geodesics. All right. So let me just say that. So, well, here's the retraction principle. So this we already talked about. And so we have this lemma that for any x in Rn-1, the vertical line t goes to x comma e to the t in the upper half space. This is a geodesic. Okay, and in the unit ball, for any unit tangent vector v in Sn-1, this radius t goes to tan h half t by 2 into v. This is in the unit ball. This is also a geodesic. Okay. So these are in the upper half space, you have these vertical lines are geodesics. In the ball, you have these radii through the origin, diameters are geodesics. Okay. And this, it's easy, it's the same argument that we used in 2 dimensions. Basically, we look at this map pi from the upper half space to the vertical xn axis, right? X comma xn goes to 0 comma xn, this projection, right? So this fixes the height, right? And so the norm of the derivative applied to a vector, the hyperbolic norm is less than or equal to the hyperbolic norm of the vector. Is this clear? Right? This decreases the Euclidean metric and it preserves the height. Therefore, it's going to decrease the hyperbolic metric. Is this clear?
Yes, sir.
And this is a retraction to this vertical line. Therefore, by the retraction principle, this vertical line is a geodesic, right? Okay, it's the same argument as in 2 dimensions. Is this all right?
Yes.
Okay, and then you take this parameterization e to the t for the height, because this is unit speed, right? The speed of this curve will be 1, all right? So therefore it's constant speed, and so it's a geodesic, right? By the retraction principle, all right? So once this is a geodesic, then we know that under the isometry from the upper half space to the ball, this goes to a radius through the origin, right? Yes, it goes through a radius, a diameter through the origin.
Yes.
So that is also a geodesic, right? And then once you know that one diameter passing through the origin is a geodesic, in the ball, you know that rotations of Rn, the group SON or ON, acts by isometries of Hn, right? It preserves the hyperbolic metric on the ball. And so therefore, every radius through the origin is a geodesic. Is that clear?
Yes.
Okay. So therefore, every radius through the origin is a geodesic. And as a corollary, we get that Hn, the upper half space, is complete, right? Because in the ball, geodesics passing through the origin are defined for all time. Is that all right? Yes?
Yes.
Okay. Now, what I'm going to do now is look at copies of H2 inside Hn, right? So if you notice, there are copies of the 2-dimensional hyperbolic plane inside the n-dimensional hyperbolic space. So for example, if I look at the subspace in the upper half space, x1, 0, 0, 0, xn, where x1 is real and xn is positive. So this will be a copy of H2 inside Hn, right? With the induced metric, this is isometric to the upper half plane, right? Is that clear? Yes?
Right.
Right? I mean, the metric here will become just dx1 squared plus dxn squared divided by xn squared. That is the metric of the upper half plane, right? This is a copy of the upper half plane inside the upper half space. Is that all right? Yeah. So we'll denote this subspace by H, okay? And now, similarly in the ball, we have a copy of the 2-dimensional ball inside the 2-dimensional disk inside the unit ball. You just look at the points with x1, x2, and all other coordinates 0, right? x1, x2, comma 0, 0, 0. So this is a copy of the disk inside the ball, right? This is a horizontal disk inside the ball. Is this clear? Yeah. And with the induced metric, it's isometric to the hyperbolic plane, to the unit plane disk. Is this clear?
Yes, sir.
Okay. So we have copies of the upper half plane in the upper half space and the unit disk inside the unit ball. All right. Now, what I want to say is that for any 2 points in the upper half plane, there is a geodesic of the upper half space which is inside the upper half plane joining x to y. Okay, and in particular, the distance function on the subspace H induced by the restriction of G naught coincides with the distance function of Hn. Okay. And geodesics of H are geodesics of Hn. That means geodesics of H with the induced metric are geodesics of Hn. So, okay, well, I didn't do this in full detail. So one thing is you have this retraction, right? X comma xn goes to, oh no, it follows from the retraction principle. Right. No, we have a retraction, a distance non-increasing retraction from the upper half space to the upper half plane H here. It's x comma xn goes to x1 comma 0 comma 0 comma xn, right? So again, this is a retraction from Hn to H, which is distance non-increasing, right? That means the norm of the derivative is less than or equal to 1, right? Is that clear? Yeah, because it decreases the Euclidean norm and it preserves the height. So norm d pi will be less than or equal to 1 everywhere. And so therefore, from the retraction principle, if I take 2 points in H, I join them by a geodesic in Hn, right? And then I apply this retraction pi to my geodesic gamma in Hn. So pi of gamma will have shorter length than gamma, right? Gamma I'll take to be a length minimizing geodesic. So then pi gamma is also length minimizing, right? And pi gamma lies inside H. So therefore, any 2 points in H are joined by a geodesic of Hn, which lies in H. All right. Is this clear?
Yes.
Okay, so let me just write that here. So, I mean, the picture is like this. So, this is the x1 axis, and this is the xn axis, right? And this copy of H is like this. Right, it's the x1 xn plane, right? This is H subset of Hn. Okay, and I have this retraction pi, right? I have pi from Hn to H. X bar xn maps to x1 0 0 xn. This is a retraction. And norm d pi v less than or equal to norm v for all v in Hn. Okay. So if I take 2 points here, say P and Q, and I have a geodesic, maybe it might go out of H, I don't know. And then this is say gamma in Hn. I look at pi composed gamma, right? This is gamma, this is pi composed with gamma. Right, so then pi composed gamma will have shorter length than gamma. And it will also have length greater than or equal to gamma. Okay, if gamma is length minimizing geodesic from P to Q, right? So it will be equal. And so this is a length minimizing geodesic from P to Q in HN implies pi composed gamma length minimizing geodesic from P to Q in H. Okay. Is this clear?
Yes.
And also if gamma in H is a geodesic of H for the induced metric, say from P to Q, okay. Then for any, so is a length minimizing geodesic. Well, okay, let me take it to be a length minimizing geodesic. Then for any gamma tilde in H n from P to Q, pi composed gamma tilde is a curve in H from P to Q. So since gamma was length minimizing, pi composed gamma tilde will have length greater than or equal to the length of gamma, right? Okay.
Yes.
So the length of pi composed gamma tilde is greater than or equal to length of gamma. And that implies, because pi is distance non-increasing, length of gamma tilde is, this is greater than or equal to length of pi composed gamma tilde, which is greater than or equal to length of gamma. Okay, so that means that gamma is length minimizing in Hn, right?
Right.
Okay, so therefore any geodesic of H with respect to the induced metric, it is locally. So now if I take, if gamma is a geodesic of H, then that means that gamma is locally length minimizing in H, right?
Mm.
But then that means that in H, for any T, if I look at epsilon small enough, then gamma is the shortest curve from gamma T minus epsilon to gamma T plus epsilon, right? It is the shortest curve in H there. So therefore, by the above argument, it will be the shortest curve in Hn from gamma T minus epsilon to gamma T plus epsilon, right? So therefore, gamma will be locally length minimizing in Hn, right?
Mm.
Is this clear? Okay, by the above argument.
Yes.
So therefore, gamma will be a geodesic of Hn. Okay.
Mm.
So therefore, any geodesic of H with the induced metric is also a geodesic of Hn. Okay. So actually, a subspace with this property is called totally geodesic. Okay. So note, I mean, this is not obvious, right? I mean, not all subspaces are going to satisfy this property.
Sir,
So yes.
don't we have pi compose gamma equal to gamma in the first part? I mean,
That's right. That's right. Pi
but
compose, no, pi compose gamma tilde I'm looking at, not gamma.
no, sir. In the beginning, before this last part that
No,
you,
no, no. And then no, here in this gamma.
yeah, this gamma.
No, this gamma it was taking in Hn, right? This
So
gamma I was taking in Hn.
gamma is uniquely length minimizing. Hn has unique length minimizing geodesic, right?
Yeah, but I'm not using that yet. I mean, I
Have we proved it yet? That's what I'm asking. No, right?
we can prove it now. We can prove it now. We can prove it now. So, okay. So first, let's note that geodesics of H are also geodesics of Hn, right? Okay.
Yeah, right. Yeah,
Now also, so therefore, so we've proved this. So therefore, geodesics of the discs of the disc in the ball, geodesics of D are geodesics of Bn. Is this clear?
Hmm.
Because my isometry will map H to D, and so therefore geodesics of H will go to geodesics of D, and geodesics of H are geodesics in Hn. So geodesics in D will become geodesics in Bn. This is clear, right?
Yes, sir.
Okay. Fine. So we have this. Now notice this is a crucial point. For any 3 points, say X, Y, Z, in Hn, there is a copy, well, an isometric copy of H2 containing them. So how do you show this? So work in the ball. Okay, so work in the ball. Okay, so in the ball, I have 3 points. So what can I do with these 3 points? Can I make my life a bit simpler? I want to show there's a copy of H2 which contains these 3 points. So what can I do to start with to make my life simpler? Yes, anyone?
Make one of the points key origin.
Right, I use an isometry to, since isometries act transitively, so without loss of generality, X is equal to the origin, right? Okay, fine.
Yes.
Okay, so now
The radius joining now.
I have 2 points Y and Z, right? And then
Yes.
what I can do is if basically I look at the vectors, so which are going the unit vectors from 0 to y, let me call that 0 y vector, and the unit vector from 0 to z, unit hyperbolic vector, right? So this is in the tangent space at the origin. So this gives me a subspace of the tangent space, right? Which is of dimension at
Which
most.
of the geodesic we are looking at, right?
Right, so I have my y and z, right?
Yeah.
I have my y and z. I take the radii, I know I have these radial geodesics, right? From the origin to y and the origin to z. So I take the tangent vectors here, right? So this will give me a 2-dimensional subspace, except for the degenerate case when they're equal, then it gives just a line. So it will give a 2-dimensional subspace, right?
Yes.
And so then we choose